Good afternoon. My name is George Parris. I'm a PhD chemist, an old PhD chemist, and I really don't know that much about physics. If I did know much about physics and consider myself to be a physicist, I probably would not be giving this presentation because I'd have too much to lose. I mean, you got to stick to the program if you're going to be in the center of things. In any event, I want to start out by talking about the history of science. Okay, I used to be, as a young guy, I thought, I don't want to know anything about the history. I don't need to know people's names. Why do I care? All I want to know is the facts. Give me the facts. I'll go forward from there. Okay. Well, it turns out that knowing something about the history can be very important for a variety of reasons. One, you might find some things that you didn't think were right and why they're not that way. Another reason is you might understand how people came about doing certain experiments and get ideas about how to do your own experiments. And of course, it never hurts to drop a few names along the way. Anyway, I ended up writing a book. I've written several books about the history of various types of science. This one is my book on the history of atomic theory. And in the course of writing that book, as a chemist, you end up having to teach a certain amount of this to your students. Thomson and Rutherford and people like that come up, the Bohr theory, whatnot. In any event, so I was generally interested or knowledgeable about it. I wanted to know a lot more about it, and I did a fair amount of research to write the book. I've even got notes here to keep my dates straight, and also try to keep you on track. There's a lot of side stories that you could go off on for a long time. In any event, I found some interesting things, and it led me to make some ideas of my own, and some hypotheses came up, which could get me in trouble if I were a physicist, but since I'm a chemist, who cares? Right. So anyway, let's go back. Historically, I could go back to the 1700s, but for brevity, let's start about 1900. Okay, if you go back into the late 1800s, very fantastic, very important time in physics and chemistry. Physics and chemistry very tightly intertwined. I'll name three names that were very important in the late 1800s. J.J. Thomson discovered the electron. Max Planck discovered that things were quantitated, that weren't just old classical physics anymore. And then Madame Curie, radioactivity. There was actually several people in each of these fields, but these are the names that sticks out. Okay. All right. Well, that's 1900s. Let's carry this forward a little bit. Thomson, of course, when he discovered the electron, there was really only one, well, maybe two natural phenomena, natural forces that people understood in the 1800s. One was gravity, Newtonian gravity, and number two was electric charge, electrostatic interactions. Okay, these two forces were one of the things known to hold atoms and subatomic particles together way up until the 1930s, 1940s, and so both chemistry and physics was tied very much to this. Thomson took this information, electrostatics, and came up with what seemed to be the most reasonable identification of the atom. Now, the physicists were still arguing about whether or not atoms existed right up until Einstein, or beyond, up until X-ray diffraction. But in any event, assuming that there were atoms, I think chemists were assuming things were atoms from 1800 on. But the physicists were not totally convinced. In any event, the Rutherford's model was what's called the plum pudding model, and it made perfect sense from an electrostatic standpoint. The electrons and the protons, or the positive charge, were bound together. The electrons were apparently plugged in like raisins in a bun or a biscuit. And so the British called it the plum pudding model of the atom. So you had this model in which it wasn't a nuclear model, it was a thing with little electrons popping out of it. And nobody knew how many electrons were in an atom or how they got there or anything else. So that was the the theory, the thought going forward. Now, Rutherford had a very good student. Excuse me, not Rutherford. Thomson had a very good student named Rutherford. All right. Rutherford originally wanted to go into the electromagnetic waves, but it turned out Marconi was much better, and so Rutherford said, hell with that. And he got off studying some of the Marie Curie's stuff. It was much more interesting, radioactivity. So Rutherford, with a guy named Soddy, did a lot of interesting work. And I can't go into all of that. But if we keep going forward, by 1909, just follow this chain for a second, Rutherford had become well known. He had a research group, and he was interested in pursuing this model of the atom. Actually, it was more looking at what alpha particles do when they fly through atoms. So he had a graduate student named Marsden. He had a postdoc named Geiger. And he said, look, Geiger, take Marsden and go over here and do an experiment where you shoot alpha particles through a thin gold foil, because we can hammer gold very thinly. And, just tell me what happens. I don't know. And so this was a very tedious experiment. It took like over a year to do. Poor Geiger and Marsden had to sit in a dark room with a zinc sulfide covered screen and a microscope watching these flashes as these alpha particles bash through the gold foil. And it's not nearly as beautiful as you see it in all the textbooks today with the 360 degrees wraparound. No, it was a flat screen, and they were watching this thing and doing all kinds of stuff. In any event, that was 1909. Now, the funny thing about this was that some of those alpha particles bounced back. Okay, this was not expected if you were talking about the Plum-Podium model. All right, the proton was just, or the alpha particle was supposed to go through, get slowed down, maybe deflected a little bit, something happened, and we would just count them on the other side. No, some of them were bouncing back. And this really excited Geiger and Marsden and Rutherford. Now, Rutherford allowed Geiger and Marsden to publish their data, but he wouldn't let them write a conclusion. All right. Rutherford spent like another year. Now, in Rutherford's defense, he was a very, very honest and very, very detailed analyst. If he hadn't been that, there's a lot of stuff going on with the atoms that back in the radioactive areas that nobody would have ever believed. I mean, he had, going back in time when he was studying radioactivity, he would have something that would turn from one element to another element and back. Who believes that? I mean, if he hadn't believed the data, and if he hadn't been very precise, nobody would have ever figured that one out. But he did. He published it. He gets credit for it. And it's the same sort of precision and detail concern that Rutherford had, I think, explains why he didn't let Geiger write a conclusion in his paper, although I think the conclusion was fairly obvious from some of the results. In any event, in 1911, Rutherford wrote a paper, said, hey, there's a nucleus in there. It's a hard, small nucleus, and most of the rest of the volume is occupied by electrons. Now, this was great news, or very interesting news, to a guy named Bohr. Bohr was from Copenhagen. He was visiting with Rutherford's group. And when this information hit Bohr, who had been working on the Balmer series and other atomic spectra, Bohr said, hey, I can now explain the atomic spectra if I put the electrons in energy levels, different energy levels, and that they're in these orbits around the nucleus. Okay, so suddenly, with Rutherford's information, Bohr was able to completely and accurately explain the atomic spectrum. This was a great breakthrough, and if anybody had any doubts about quantum theory and whatnot, by now they were sold on this idea. So that was about 1911. Now, in the meantime, of course, Curie's work in France gave way to work by Meitner and Hahn, Lise Meitner and Otto Hahn in Berlin, Germany. And Geiger was German, and he apparently bounced back and forth amongst all the top groups. He was a really very good pair of hands, apparently. And he went back to work with Meitner, and he apparently took a fellow by the name of Chadwick from Rutherford's group back. So they're back working with Meitner and Hahn. And in 1914, something very interesting happened. Rutherford had already identified beta decay, beta particles coming out of atoms. They were obviously coming out of the nucleus of atoms. And everybody was assuming that this must be a quantum effect. You know, like there's a change from this to this, and everybody expected this to be a quantized phenomenon, and expected all these electrons to come out at the same energy. From any particular atom, they'll all come out the same energy. But in 1914, Geiger and Chadwick realized, hey, that ain't the way it is. We're getting, the electron energies are a spectrum. I'll stand up here for a second. Well, no, I won't. Get too complicated. On the chart behind me, I've got a graph. Basically what they do, they plot on the vertical axis, you plot the probability or the relative number of atoms. And then on the horizontal axis, you plot energy. And what you find out is that there's a maximum energy for these electrons. So the probability of finding an electron goes to 0 with some energy, and it gets bigger as you get to lower energies. And there's a little dip right at the end. All right. And so there's a spectrum of energies of all these electrons coming out. Nobody could explain that. This is supposed to be a quantized world, and suddenly they weren't. So that was exciting to people. Well, interestingly enough, 1914 is an important year. World War I started. All of Europe shut down. 1917, you had the Fort Riley flu. I'd say that because it started at Camp Funston in Fort Riley, Kansas, not in Spain. I'm sorry. Spain gets a bad rep. Anyway, so the war went on till, I guess, 1918, 1919, something like that. And Chadwick was interned in Germany from 1914, 1918, and he was interned with a guy named Ellis. Don't recall exactly Ellis's history to that point, but he and Chadwick hung out, and Chadwick and Ellis then came back to the States, or back to Britain. Now let's go back a bit and talk about Planck. Planck, of course, identified quantization, and nobody believed him. Planck was a very well-respected physicist, but he was very nervous about saying, hey, you can't just be any wavelength, you just can't be any energy. You've got to have discrete energy levels. And there was this young man named Albert Einstein who was just a happy-go-lucky physicist out there with a sweetheart who also was a physicist. And Einstein, in 1905, published, I think it was 5 very, very important papers. Just his, it's like he was not tied to everybody's thought process. The two that most people remember were the theory of relativity and also what's known as the photoelectric effect. Now, the photoelectric effect had been discovered earlier by, I guess it's Heinrich Hertz, and other folks had worked on it, but nobody quite understood it. I'm not going to go into what it was. It's a whole other interesting story, which you should study in physics and history of physics. In any event, so Einstein published his theory of photoelectric effect, which was just what Planck needed, because he basically explained the photoelectric effect using Planck's quantized theory. So Planck suddenly, by the way, Einstein didn't actually do experiments, he just had a theory about how things should work. Anyway, Planck was thrilled because Einstein had used his idea of quantization to explain a physical phenomena, which sort of made it easier for Planck, although Planck was already pretty well known, to not feel like he was about to get shot out of a cannon by the physicists. In any event, this Planck reached out and raised Einstein up. Okay, never underestimate the importance of having somebody important say you do good work. Now, Einstein was clicking along in the, say, 1905 to 1920 time frame. All of his theories were sort of coming out to be true, and people were getting excited about it. In particular, Einstein, I think, favored over everything else relativity. And a fellow by the name of Eddington, a well-known astronomer, basically did some experiments, went, I think, to South America or Africa or someplace, and took some photographs in the middle of an eclipse and proved that Einstein was right about relativity, at least that part of it. This is 1919. Well, Einstein was very excited about that because he was hoping to get a Nobel Prize, among other reasons, because that wonderful physicist wife he had divorced her and had promised her the proceeds of a Nobel Prize. And so he was going, like, let's get that Nobel Prize, pay off my ex-wife, and get out of here. So anyway, this was 1919. Well, Einstein, unfortunately, he was well known and very respected among some people, but he was Jewish, and this was a political issue, and it was also impacted the way science was looked at. This was Jewish science. It wasn't selling well in Germany at the time. And so he had hoped to win the 1920 Nobel Prize based on the 1919 observations by Eddington. And it turns out, here we come back with Pauli. Remember Pauli? I guess I didn't mention Pauli. Did I mention Pauli? Anyway, 1900 was a very good year for physicists, by the way, 1900, 1901. In 1900, Pauli was born. That would be Wolfgang Pauli. 1901 was Werner Heisenberg was born, and Enrico Fermi was born. Three very important names that come up later. Pauli had sort of, he was well connected, got a good school, was doing yeoman's work in physics, but he wasn't a genius. Actually shared lab space, I guess, with Heisenberg. Heisenberg is reported to have described Pauli as sort of a playboy guy, stays out all night and drinks, hangs out in bars, comes in about noon the next day, makes his research director unhappy with him, goes out again, hangs out the next night, you know. So Pauli was not exactly your most studious student. His thesis was nothing great in any event. So, but here's what happened. He was a late-term graduate student, and his thesis advisor said, hey, why don't you write something about Einstein's theory of relativity? Just write a popular paper that we can, so everybody can sort of understand this. So Pauli goes and writes this paper. It was not research, it was just a description of Einstein's work in terms which a lot of people could understand. And this got widely circulated. And Einstein realized that this is helping me win the Nobel Prize. So Einstein basically then writes glowing reports about the report and about the guy who wrote it, Pauli, who's really nothing special. But I mean, Einstein was basically trying to grease the skids for his own advancement with the Nobel Prize. But in the process, he made a big deal about Pauli. This created Pauli's reputation as being a genius. All right? That was 1920-21. Well, it turns out that the Nobel Prize was not offered in 21 because of politics. It was awarded to Einstein in 1922. It was a 1921 prize awarded in 1922, and it was awarded to him not for relativity, but rather for the photoelectron effect, which was more acceptable to the mainstream of physics in those days. Okay, well, going back to the Rutherford group, Chadwick and Ellis had been interned in Germany through the war, 19 1914, 1918. Just before that had happened, Chadwick and Geiger had discovered that, hey, these electron energies are not a single line, it's a continuum spectrum. So 1920, Rutherford starts looking at this and says, hey, these electrons are not just running free in the nucleus. They must be actually attached in there some way. And he proposed something called the neutral doublet hypothesis, which I think is really a pretty good idea. It's his idea is that you have a particle that is a proton and electron together. It's neutral, and it behaves as a single particle, and it's in the nucleus. And that out comes the electron, and you get a proton. The atomic number goes up one step, etc. Now, everybody started studying beta decay at this point. You had Meitner and her group over in Germany. You had Rutherford and Ellis in Britain. And from 1925 to 1927, and there's a lot of going back and forth with this, okay? They were really puzzled by this. They spent 3, 4, 5 years studying this. And they disagreed about certain things. They disagreed about the relationship of X-rays to beta decays and all that kind of stuff. And finally they found, I guess it's bismuth-210 gives off a beta particle with no X-ray. And so that made us a case that could be studied very, very isolated. Got this one isotope, excuse me, I'm a chemist, not a, they got this one isotope that gives off a beta with no alpha and no gamma, so it was simple to study. And they built exotic essentially calorimeters that they could measure the amount of energy for these things. It was like thousands of degrees type changes in temperature. But ultimately, by 1927, the Rutherford group and the Meitner group, Ellis with Rutherford, had sort of come to agreement that it happens, it's happening, we don't know why, we think it should be quantized, but it's not. But we both agree that the experimental says it's a continuum. And this became a big problem. It's like, how do we account for this? Now, I'll explain that in a minute, but they didn't understand at the time. Part of the, I will give a hint here. At that point, the nucleus was considered to be so small that it was not treated as having much volume. Although George Gamow, about this same time, was talking about a liquid drop model of the nucleus, but it was still real tiny. In any event, there was a very important meeting. Remember a guy, Pauli? Let's talk about Pauli a second. Pauli was not in the mainstream. He was not a good experimentalist. He was a disaster from the experiment. He was not a particularly good mathematician. He was not much of anything, honestly. And he ended up, after World War I, there was a lot of poverty in Germany. There was a lot of destitute people. He had, because he was a college professor, he had a steady income. He was in Berlin, and there was lots of poor single women coming in there to earn a living. And in 1929, I guess it was December 29, he married one of these women, who is, I guess she's uncritically defined as a dancer. I think she was probably a prostitute, but that's just me. Okay. So anyway, so he was married to this dancer, and he ended up, now Pauli was also, I mean, he was probably a quasi-drunk. Okay. They ended up in Austria, where I think Pauli was actually from. And she divorced him in literally a year later, like December or November of 1930. She said, "Go away, I don't need you anymore." Pauli, who is at this point concerned about the Nazis rising up in Germany, moves to Switzerland. He's in Zurich. he's totally out of the mainstream of physics at this point. He was a ne'er-do-well chemistry professor, excuse me, physics professor in Berlin. Now he's like way out in the court or someplace. He is desperate to get visibility back with this group. The patina that was put on him by Einstein is worn off. He's nothing special. Hasn't done any important research, hasn't done anything else. He's in Zurich trying to hide from the Nazis. Okay, so there's this big meeting, and I forget if it was in Germany or I guess it's in Tübingen, depending on how you pronounce the German. Tübingen. And so there was this big meeting there, and Pauly knew about it, but he wasn't invited. He was desperate to get these people's attention, so he sent a telegram to, I think the telegram went to Meitner and to Geiger. And the telegram was I think it starts off with, "Dear radioactive people," or something like that. And he says, "I've got this great idea. I can solve your problems." It says, you've got this continuum spectrum, no problem. All you have to do is hypothesize that there's a particle that you cannot detect. It has no mass, it has no charge, but it leaves at the same time that the electron leaves, and it takes away part of the kinetic energy and momentum, and now you can explain your spectrum, your energy spectrum, because it can divide it up any way it wants to. Well, of course, nobody thought that made any sense at all. You don't have a neutral particle that can't be detected, that doesn't have any mass, that can carry away kinetic energy. That flies in the face of everybody's physics. Nobody gave it the time of day, and nobody thought much of it, except Pauly. Okay. Now, that was December 5th, 1930. Pauly managed to get a trip to the United States, and he ends up in Pasadena, California, where there was physics research going on. And in 1931, this was actually June of 1931, he gave an interview. You know, he's from Germany. He's a physicist from Germany. People think he must be genius. Okay, so he's in California. He gives a talk to an interview to a newspaper reporter. The newspaper reports it up, saying, "Hey, Dr. Pauly from Germany has discovered the neutron. It's a particle that explains the beta decay phenomenon." Okay, so that became, the neutron idea got out there, and it got out there because of sensationalistic reporting. I don't know. So anyway, this is going on, and this is June of 1931. And in 1932, Chadwick, back over in Britain, doing some exotic chemistry, actually physics, discovered the real neutron. Okay, so the real neutron is a real particle. It has real mass, and it can be detected, and it was not easy to detect, but it can be detected, and it can be accelerated various ways. And so it was identified as the neutron, and it had a lot of mass. So when this happened, the neutron, that Pauly's particle, was demoted to being the neutrino. It's a small particle, okay, a massless particle. Now, you know, still nobody much cared about neutrinos. It's like, what's that? Now we go back and we pick up Fermi. Fermi was a bright guy. He earned a lot of credit for his brilliance as a mathematician and for various things he did as an undergraduate, graduate. But Fermi was about to launch himself into oblivion, as far as I'm concerned. The first thing happened was in 1934, using his math skills. He loves to write, you know, do linear algebra with Greek symbols and stuff, you know. physicists are into that, mathematicians are into that. So Fermi writes this paper in which he tries to explain quantum mechanically what the neutrino is. And he does his math, which I don't follow, but I can read these conclusions. And it boiled down to this. He says something to the effect that if the neutrino's mass is 0, then I can make a curve that looks like the experimental curve for the beta decay. That's the sum of the paper. Now, that paper he submitted first to Nature, and Nature rejected his paper. Nature basically came back, as I recall, the comments from the reviewers says this is way too far from reality. Okay, nobody, I mean, Nature's still not believing this stuff. However, Science, the American paper, Science, accepted this paper and published it. Now, Science is not, in my view, has published, this was probably, maybe the first, but I know of at least 2 other cases where Science was completely hoodwinked by false data and gave a lot of attention to, published a number of papers of this from a guy who was like faking the data. And another one in which a lady had absolutely no clue of chemistry and wrote a paper that got published in Science, and it created a landslide of other stuff. People love to get published in Science, but it's got some problems as far as that's it. And this was one of them. Actually, I consider this to be the biggest mistake of Fermi. All right. Anyway, this paper got published. Now, when he, at this time, 1934-ish, he was doing some very credible research, very interesting, very high visibility research. Once that neutron had been discovered by Chadwick, it was realized, hey, this neutron can penetrate into a nucleus, whereas a proton veers off, an alpha particle veers off, but a neutron is not repelled by the positive charge of the nucleus and could get in there. And so the idea is we'll shoot neutrons at nuclei, and maybe they'll be picked up, create a higher isotope. If it undergoes beta decay, out comes the electron. I got a new proton. Guess what? I just increased 1 atomic number. If I start off with uranium, I make higher atomic number elements. And so Fermi was publishing papers claiming to make transuranic elements by shooting in a neutron, and then he didn't do chemistry very well. He was a physicist and a mathematician. He didn't do chemistry well. He didn't analyze these chemical products that were coming out of there. He had radioactivity and stuff, but he knew he didn't have what he started with, but he didn't know what it was. Anyway, he got lots of attention, lots of publications. That went on from 1934 to 1938. In 1938, he was nominated for and won the Nobel Prize for transuranics. That was like in probably like November, early December 1938. Gave his big talk. So you can find the videos of this. Within a month, Otto Hahn, now working in Germany, Meitner had left Germany. This was 38. She was in Sweden, I guess. But Hahn, collaborating remotely with Meitner, he and I forget his colleague were doing, Hahn was a physicist, but he had a good chemist. Actually, Hahn was a chemist too, I guess. They were doing good chemistry, and they were trying to analyze the products of a neutron capture experiment. And they didn't know what they got. First they thought maybe they had radon, and then they said, well, maybe this is not radon, maybe this is barium. And they were doing wet chemistry tests for these things, and you have to make this stuff, precipitate it very carefully, do all kinds of exotic, tedious chemistry. And eventually they decided, we got barium, we're not making heavier elements, we're making lighter elements. The nucleus is not gaining mass, it's splitting. This was you know, this is basically nuclear fission. Meitner, Otto Hahn published a paper early. It actually got published early. I guess it was 1939. Meitner published a paper shortly thereafter. Meitner's given a lot of credit for that, but that paper that she published doesn't really say the things that people say she published. I mean, it was a very vague paper, went off in various directions. I don't think it proved much of anything. Hahn's paper was the paper that's important. By the way, Hahn won a Nobel Prize. Meitner was not on that Nobel Prize, given no credit. And you have to remember, he received the Nobel Prize in chemistry for his chemistry. Now, if the physicists had thought that Meitner did a great job, they should have given her a Nobel Prize in physics. But they didn't, because I mean, if you read the papers, it really isn't that big a deal. Recent years, you know, there's been a lot of interest in women in science, and so people have looked at Hahn, who was with the Nazis in Germany, have tried to make Otto Hahn to be a bad guy. He was actually a good guy. And he certainly, Meitner certainly did not deserve to be on his Nobel Prize. But that's, again, my opinion. Again, if I were a physicist, if I were young, I probably couldn't say that. Okay, so anyway. That's where we find ourselves with the atomic story. Now, exactly what happened here. Basically, because there's one more step to this process. Fermi has dignified the crazy idea of Pauli, that there's this neutrino, it's got no mass, it carries away kinetic energy, it's got no charge, it's just out of space, it just does its thing. And the only reason it was ever introduced was because you have a spectrum of energies, kinetic energies, of these beta electrons coming out. Well, it didn't take me very long. Now, here's the problem I see. At the time that was all going on, the nucleus was a new idea, and it was very small. And everybody seems to have treated it as though it was a point. We talk about, you got a nuclear charge, point charge, you have an electron, that should give you a nice change in energy. I mean, you've got electrostatics, quantum theory, all that stuff, no problem. But Gamelot had already started raising the idea that this nucleus is not a point. One nice thing about a point charge is if you have an acceleration against it, it's always going to go through the center of mass, all right, for one thing. So you don't have to worry about any torques on that nucleus, which is you start thinking about it. First thing, okay, if that electron, that proton, that neutral doublet, which we call a neutron now, if that is split someplace other than the center of mass of the atom, and that electron goes flying out, the trajectory of the electron does not necessarily pass through the center of mass of the atom. So there must be a torque applied to the atom. Now that torque is going to take care of some of that recoil energy that we've been thinking about. The other issue, and I think the more important issue, though not the only issue, is that Gauss's law. Those of you who have studied electricity or electronics have heard about Gauss's law. For those of you who are not into that, let me think about gravity. If you were a person and managed to go to the center of the Earth, you would have no weight, because the mass of the Earth, assuming it's a perfect sphere, is pulling you in all directions, and they all balance out. Same thing, if you happen to be a neutron and you are in the center of a nucleus with a spherical charge around you, then when you decay, you feel no electrostatic effect. It's just like you were a free neutron going off here. And so if this is a quantum phenomenon where a neutron converts into a proton and electron, you find out there's a loss in mass, which must be accounted for in energy someplace, and that's primarily the energy in the electron, and that is that one single energy that everybody was looking for. But if you take that same neutron and you move it off the center of mass, center of charge, now the charge that's inside that radius is going to affect that neutron. And so when it goes off, you've got a electrostatic charge that is not the same as the charge of the nucleus go out. Now think about this for a while. It turns out, let me go back another step here. Think about the Big Bang. Big Bang apparently produced electrons and protons. Why? Because there's no neutrons out there. There's no neutrons are not flying around in outer space. It turns out neutrons, if they were formed in the Big Bang, they're unstable. If you have an isolated free neutron, it decays about, I guess, 5 minutes, 10 minutes, something like that. It goes away, turns into electron and proton. Now, when that happens, by the way, I've never found anybody writing about the neutrinos that are supposed to be released when a free neutron does its thing. Why not? Why is that just one energy of those electrons? Why not a spectrum of those? I don't understand. In any event, you can readily explain the spectrum, the beta electron spectrum, if you just say, hey, sometimes the nucleus is near the center of the atom and sometimes it's not. And it turns out that if neutrons are not stable by themselves, why do we have neutrons at all? Well, it turns out that when your hydrogen, which is most of the mass that was produced in the Big Bang, comes together into stars, if you have a big enough star, you start putting pressure on the hydrogen. At some point, the hydrogen actually turns into a metal. It goes from a gas to a liquid to a metal. And then if you go a little bit further, you can actually crush it. There's a P delta T phenomena. Pressure, temperature, or pressure volume is an energy term. You can calculate how much pressure it would have to take a neutron, or excuse me, a proton, an electron, that is a hydrogen atom, and converts it into a neutron, and that's about what you see. And so when you have these very big, massive stars, you get these neutrons formed in the star, and when the star is supernova, the neutrons get caught up with protons and electrons to become atoms. It is only in some cases that there's a big enough nuclear charge to prevent the neutron from decaying and leaving, or they're spinning out electron and leave. And so what's happening here, the reason we have neutrons in nuclei is that some of these nuclei, there's no place in the nucleus where the electron can escape. In others, it can escape in some places, but not in others. They're radioactive beta decayers. And in some cases, they just never escape. And in some cases, they're simply not stable. They just go away. Okay? So that seems to be what's happening. I mean, the neutron by itself is not stable. It must be, there's something about the nucleus that's holding in it. It's obviously the nuclear charge is preventing the electron from getting away. Now, let's go to my theory, my hypothesis here. I'm not sure how much of this you can see. All right, I don't know if you can see this very well. This is a classical experimental curve. This is the probability of an electron coming out and this is the energy electron. You'll notice that way out here you have something called Emax. That's the maximum kinetic energy that a beta electron would have. It has a certain value, which is in the 1.0 to 1.2 MeV range. And then as you get to lower energies, you get more and more of these things, and then you have a little drop off at the end. Now, I have cleverly, I take great credit for this, I took this curve and I superimposed it on a model of a nucleus. Here we have a nucleus, and I put this curve, there's my energy axis, here's my probability axis, and here's this dashed line is my probability axis. And if you're right in the middle of this atom, right in the middle of this nucleus, there's all of static charges balance out, and so you get the highest energy electrons out. Now, as you go further out, you get, for example, if you're on this circle, everything within that circle, the darker material, is charge that will try to retain that electron. That electron goes flying out, and this electrostatic charge tries to recover it. Now, the probability of that happening is larger than probably being right in the nucleus. Okay, being right in the nucleus is probability almost zero, but as you move further out, you have each shell that you move into is bigger. There's more volume in that shell, and so the probability goes up as you go out, except perhaps around the edges. The neutron has a certain amount of volume, a certain diameter itself, and it's compared to the nucleus, it'll overlap, and so at some point you start getting a little drop off. So I believe we're talking about a very simple phenomenon of Gaussian electrostatics, in which you could explain the classical beta spectrum purely on the basis of electrostatics. I have taken the numbers for the bismuth 210 situation and divided it up. There's a binding energy in there. There's what I call a neutron inflation energy, in other words, a neutron becoming a hydrogen atom. Then we have a hydrogen ionization energy, and then we have the observed energy of the kinetic energy. And so you look at these four numbers, and you can explain this number here. If you look at these four numbers, the math adds up. Now, there's another issue. You do have the potential of having a torque. If this electron goes flying out here, this is going to tend to twist this nucleus. And so you can, I'm sure you have some sort of a nuclear magnetic resonance phenomena going on here, where, okay, we have an electron flying out, we have a current going in that direction, and that creates a induced magnetic moment, which we should be able to observe. So that's my hypothesis, and if I were a physicist, I'd never tell you that, because physicists, I've sent this to physicists, I've asked people to consider it, to comment on it. Physicists just tell me I'm crazy. Neutrons exist, neutrinos exist in their world, and typically when they do that, they cite the work of Cowan and Raines. Who are they? Well, they were guys who worked for the federal government, Department of Energy now, whatever it was back in the day. Right after World War II, they started off at Los Alamos. They worked together out there, tried to prove that they had an interesting idea. He said, if this neutrino exists, we can make it do some reactions and we can get something observable statistically. Okay, so they tried to make the statistics work at Los Alamos. It didn't work. They went up to Hanford. They were up at Hanford. They tried to make it work at Hanford. Didn't work at Hanford. They finally came down to Savannah River in South Carolina, tried and worked very hard, made a number of adjustments to the experiment, and finally said, we have a statistically significant experiment. And they published papers. And ever since then, people have been looking for neutrinos. we're spending, I think, probably billions of dollars looking for neutrinos. And every time it turns around, it turns out to be an embarrassing particle. At one point, people were concerned that the sun had stopped working because they weren't seeing a big flood of neutrinos from the sun. And the physicist said, oh my God, the neutrinos are not just zero mass, but they are variable mass. And that explains why we don't see them from the sun. And then there was a case where they were trying to shoot neutrinos through the Earth's core to the, from one point through the part of the Earth's mantle from one point to another point. And they were getting there faster than the electronic signals were getting there. And they said, well, this must be transluminal. And that was really worrying people if we could go faster than the speed of light, if those neutrinos could go faster. That changes a lot of stuff. And so they walked around and they looked at it and they thought about it a long, long time. And they said, well, we think we have redone our model here and we've redone our hardware. And there was a loose connection. I love it. And now we're not seeing that phenomenon, so it's not moving faster than the speed of light. We're all safe. And then there's the supernova problem. When supernovae go off out here, they're supposed to hit us with neutrinos. But we've had supernovae that have been registered. And while we've got neutrino traps out there. And the neutrinos get here before the light. But they say, well, what's happening is that neutrino, when that supernova occurs, that neutrino is trapped inside, or excuse me, the light is trapped inside, it's bouncing around. And the neutrinos, they don't interact with matter, so they come out first, and they get here first. They'll get here hours before the, and it's supposed to be a straight line. It's supposed to be a single pulse. I'm saying like, whoa, this supernova process occurs over minutes, years, hours, whatever. It's not all at once. I mean, it's not instantaneous. It's happening over a period of time. We should, and as it's expanding, we still have these same chemical, nuclear reactions going on that should be generating neutrinos. So why do we see maybe a pulse, but then a long tail? So nobody's explaining these things. It's just they're out there. And what I keep saying is, okay, maybe in my lifetime, I'm 74 years old. It's 19. What is it? It's 2021. Maybe before I die, one of these big stars out there that they expect to supernova fairly close by, maybe one of those guys will go off, and we will. If all these neutrino traps don't see anything, it's going to be kind of embarrassing for these people. If we get a big flash in the sky and the neutrino detectors haven't budged or didn't budge early, it's going to be embarrassing. But I'm sure the physicists will find a way to write a proposal and get more government money. We're spending amazing amounts of money trying to detect neutrinos. That's about all I've got to say. I will close with this one thing. Rutherford actually had Rutherford's a really bright guy, and one of the things he said, I found this quote someplace along the way. Rutherford said, if you have to rely on statistics to prove your theory, you need a better experiment. And that was Rutherford's idea, and I would agree, because I think what's happening in these statistical experiments, they do it and they keep tinkering with it and they don't get the results they want. They keep tinkering with it, and eventually they get bored and they say, we have our peak, let's stop collecting data and publish a paper. And if you just kept collecting data for a very long time, they found that was just a statistical anomaly. But anyway, that's my hypothesis. That's I don't understand why this phenomenon wouldn't explain what's going on. And if that explanation had been proposed in 1932, 1929, whatever it was, then there never would have been a Pauli. There never would have been Pauli's neutrino, and it never would have become this issue. But they just didn't think about the nucleus not being a point mass, point charge. Have a great day.